Welcome back to the deep dive. We're here to take complex subjects and, well, make them make sense in conversation. Today, we're getting right into the core of how materials, specifically metals, handle the forces acting on them. Think bridges, planes, engines, our mission to really decode the fundamental mechanical properties using Callister and Rethwisch's material science and engineering as our guide. By the end, you'll get why knowing this stuff is absolutely crucial for engineers trying to prevent, unwanted bending or even catastrophic failures.
Absolutely. I mean, think about it. Metals in the real world are constantly under load. An airplane wing flexing, suspension bridge cables holding up tons of weight, like those bridge cables, they're under immense tension, pulling forces. Engineers have to know exactly how that metal will respond over time. We're talking about stiffness, strength, hardness, ductility, toughness, all these key properties. And we figured these out through carefully designed lab tests, tests that mimic real life, often standardized by groups like ASTM.
Okay, let's unpack this then, starting right at the foundation. Stress and strain. How we actually quantify force and response.
Right. So fundamentally, loads can be applied in a few main ways. You've got tension, which is basically pulling something apart, making it longer.
Like stretching a rubber band. Yeah.
Exactly. Then there's compression, pushing it together, making it shorter. And shear, where forces act parallel, kind of sliding one part past another. Think of like pushing the top of a deck of cards sideways.
Okay, sliding. Got it.
And we should also mention torsion, which is basically twisting. It's a type of shear really common in things like drive shafts or axles.
So how do we measure how a metal reacts to, say, tension?
The classic tension test. So picture this. You've got a testing machine, right? And it grips a specially prepared sample. Often it's shaped like they call it a dog bone. Imagine a round bar that's thinner in the middle with a uniform section there.
Like an hourglass almost, but thicker at the ends.
Sort of, yeah. The key is that narrow middle part. It makes sure the deformation and eventually the break happens right there, not where the machine is gripping it. The machine pulls it slowly, steadily, increasing the force. A load cell measures that force, and an extensometer measures exactly how much it stretches.
Extensometer. So that measures the extension, the strain.
Precisely. But we need to normalize those measurements. We don't just talk about force, we talk about engineering stress. That's sigma. It's the force applied divided by the original cross-sectional area of the sample. Units are usually megapascals, MPa, or sometimes psi-high.
Okay, so stress isn't just the force, but force per area. Makes sense. Standardizes it.
Exactly. And for the stretching part, we use engineering strain, epsilon. That's the change in length divided by the original length. It's unitless, a ratio, though sometimes you'll see it as meters per meter or percent strain.
So compression tests are basically the reverse, pushing instead of pulling.
Pretty much. You get shortening instead of elongation, and by convention, we usually call compressive stress and strain negative.
And shear. How do we define stress and strain there?
Similar idea. Shear stress, tau, is the force acting parallel to the surface, divided by the area of that surface. Shear strain, gamma, is related to the angle of distortion, specifically the tangent of that angle. But here's something really interesting. Inside the material, it's not always just pure tension or compression, even if that's the external load.
How so?
Well, imagine that tensile specimen being pulled. If you mentally slice through it at an angle, that simple tensile force actually creates both a normal stress, pulling perpendicular to that angled cut, and a shear stress, acting parallel along the cut. It's a reminder that internal stresses can be complex.
Right, okay. Now, you mentioned stretching a rubber band. It snaps back.
Yeah.
The elasticity, metals do that too.
They do, absolutely, up to a certain point. For most metals at relatively low stress levels, stress and strain have a direct linear relationship. This is Hooke's law, you probably heard of it. Stress equals E times strain.
E, that's the important one, right? The modulus.
That's Young's modulus, or the modulus of elasticity. E is the measure of the material's stiffness, its resistance to stretching elastically. On that stress strain plot we mentioned, this elastic region is a straight line, and E is simply the slope of that line. Crucially, if you remove the load here, the material goes right back to its original shape. It's non-permanent deformation.
And this ease varies a lot between metals.
Oh, hugely. Like magnesium is relatively flexible, around 45 gigapascals. Tungsten, on the other hand, is incredibly stiff, over 400 GPa. Big difference. Now, some materials, like cast iron, don't have a perfectly straight elastic line. It might curve slightly. In those cases, engineers might use a tangent modulus, the slope at one specific point, or a secant modulus, an average slope.
And the stiffness, it relates back to the atom somehow.
Deeply. Young's modulus basically reflects how strongly the atoms are bonded together. Think of tiny springs between atoms, stiffer springs mean a higher E. And it's important to remember E usually goes down as temperature goes up. Materials get a bit softer, less stiff when hot.
Okay, makes sense.
We also have a shear modulus, G, for elastic behavior in shear. Same idea. Shear stress equals G times shear strain. G is the slope in the elastic part of a shear test. There's also a tiny effect called anelasticity, where the elastic strain takes a little time to happen or recover, usually negligible for metals, but it exists.
Okay, but here's something I've always wondered. When you stretch something, like pull on it, it gets longer, obviously. But doesn't it also get thinner?
Ah, yes. Excellent point. It absolutely does. That phenomenon is quantified by Poisson's ratio. It's symbolized by nu. It's defined as the negative ratio of the lateral strain, how much it shrinks sideways, to the axial strain, how much it stretches lengthwise.
Negative ratio. Why negative?
Just a convention to make Poisson's ratio itself a positive number. Because if axial strain, stretching, is positive, lateral strain, shrinking, is negative, and vice versa. So the minus sign cancels out. Imagine pulling that dog bone sample. As it gets longer, its diameter gets smaller. Poisson's ratio tells you how much smaller.
And is there a typical value?
For most metals, it's usually somewhere between 0.25 and 0.35. So it shrinks laterally, but not as much as it stretches axially. And interestingly, for isotropic materials, ones with the same properties in all directions, these elastic constants, E, G, and M, are all related. If you know any two, you can calculate the third. Very handy.
Okay, so that covers the springing back part.
Yeah.
But what happens when you pull too hard? When it doesn't spring back?
Right, that's when we transition into plastic deformation. This is permanent, non-recoverable. The material changes shape for good. On an atomic level, it's not just bonds stretching anymore. It's atoms actually breaking bonds, moving past each other and forming new bonds in new positions. Large-scale movement.
And the point where this starts is yielding.
Exactly. Yielding marks the onset of plastic deformation. And this is incredibly important for engineers. Why? Because most structures are designed to operate within the elastic region. Permanent deformation usually means the part isn't working as intended anymore.
Okay, so how do we define that yielding point precisely on the graph?
Well, the very first deviation from the straight line is technically the proportional limit, but it's often hard to pinpoint exactly. So the standard convention is to determine the yield strength, sigma, using the 0.002 strain offset method. You go to 0.002 on the strain axis, that's 0.2% strain, draw a line parallel to the initial elastic slope, and where that line hits the actual stress strain curve. That stress value is your yield strength.
Ah, okay. It's a standardized way to define the start of significant plastic flow.
Precisely. Now, some materials, notably some steels, do something a bit different. They show a yield point phenomenon. The stress hits an upper yield point, then suddenly drops to a lower yield point, and then might fluctuate a bit before rising again. In these cases, we usually take the average stress during that lower plateau as the yield strength because it's more consistent.
So yield strength is basically the stress limit before permanent damage occurs. That sounds like the most critical strength value for design then.
In many, many cases, yes. It's the measure of resistance to permanent deformation. After yielding, though, the stress usually keeps going up on the engineering curve. It reaches a maximum point. That peak stress is called the tensile strength, or TS.
The absolute maximum stress the engineering curve shows.
Right. And right around that point, something visually dramatic happens necking. The sample starts to get noticeably thinner in one localized spot. All the deformation then concentrates in that neck until, eventually, it fractures.
So why isn't tensile strength the main design parameter? It's the highest stress value.
Because by the time you reach the tensile strength, the material has usually undergone significant plastic deformation. It's already necking down. For most applications, that amount of deformation means the component has effectively failed, even if it hasn't broken in two yet. Yield strength is about preventing any permanent change.
Okay, that makes sense. Beyond just strength, though, how much can it deform before it breaks? How much give does it have?
That property is ductility. It's a measure of how much plastic deformation a material can withstand before it fractures. The opposite is brittle. Brittle materials like, say, glass or a ceramic fracture with very little or no plastic deformation. If you look at stress-strain curves, a ductile metal has a long region after yielding before fracture. A brittle one just goes up in the snaps.
How do we put a number on ductility?
Two common ways. Percent elongation, percent EL. That's the percentage increase in length right at the moment of fracture compared to the original length. And percent reduction in area, percent RA. That's the percentage decrease in the cross-sectional area at the point of fracture, right in the neck. %EL can depend a bit on the origin sample length. %RA is generally more consistent.
And ductility is good, right? Makes materials more forgiving.
Very much so. It's crucial for design and manufacturing. Ductile materials can often redistribute stress locally, preventing catastrophic failure from small flaws. They give you warning before they break.
Okay, let's talk energy. Can materials store energy?
Yes, in different ways. Resilience is the capacity to absorb energy elastically and then release it when unloaded, like a spring. The modulus of resilience is the actual amount of energy per unit volume needed to stress it right up to the yield point. Visually, it's the area under the stress-strain curve only in the elastic region. Mathematically, it relates to yield strength squared divided by Young's modulus. So good springs need high yield strength, but maybe a lower modulus to store more elastic energy.
And what about absorbing energy before breaking, including the plastic part?
That's toughness. For static loading, it's the total ability to absorb energy and deform plastically before fracture occurs. It's represented by the total area under the entire engineering stress-strain curve right up to the fracture point. So, tough materials need a good combination of both strength and ductility. You need to be able to withstand high stress and deform significantly.
Strength A and D ductility. Got it. Now, earlier you mentioned the engineering stress curve might be a bit misleading after necking starts.
Right, it looks like the stress is going down, like the material is getting weaker. But that's only because we're still dividing the force by the original area.
But the area in the neck is shrinking rapidly.
Exactly. So to get a truer picture of the material's behavior, we use true stress. That's the applied load divided by the instantaneous actual cross-sectional area, AI, at that moment. And similarly, true strain, NI, uses the natural logarithm involving the instantaneous length.
How does the true stress curve look compared to the engineering one?
If you plot them side by side, the true stress curve keeps going up after the point where necking starts on the engineering curve. It doesn't show that apparent drop. This reflects the fact that the material in the neck is actually getting stronger due to strain hardening, even as the overall sample is heading towards fracture. It's a more accurate representation of the material's intrinsic response.
Strain hardening. So deforming it makes it stronger.
In the plastic region, yes, that often happens. We sometimes use a strain hardening exponent N to describe that relationship between true stress and true strain mathematically. And one more point here. Even after plastic deformation, if you unload the material, there's some elastic recovery. It springs back a little bit along a line parallel to the original elastic slope. The plastic deformation stays, but the elastic part recovers.
Okay, fascinating. Let's switch gears slightly. What about just pressing on the surface, measuring resistance to dents or scratches?
That's hardness. It's specifically a measure of resistance to localized plastic deformation at the surface. Forget the old Mohs scale for minerals. For engineering, we use standardized indentation tests.
Why are hardness tests so common?
Several big advantages. They're usually simple and quick to perform. They're relatively inexpensive. They're often considered non-destructive because they only leave a tiny indent. And crucially, hardness values often correlate really well with other properties, especially tensile strength.
So you can estimate strengths from a simple hardness test. Cool. How do these tests work?
The most common are the Rockwell hardness tests. They're popular because they're fast and simple. They use either a small steel ball or a diamond cone, called a braille, as the indenter. You apply a small minor load first, then a larger major load. The hardness number is based on the difference in penetration depth between the minor and major loads. There are different scales, like Rockwell B or C, depending on the indenter and load used.
Okay, Rockwell uses depth. What else?
There's the Brinell hardness test. This one uses a larger tungsten carbide ball, usually 10 millimeter diameter. You press it into the surface with a specific load for a set time, then measure the diameter of the indent left behind. The Brinell number, HB, comes from the load and that diameter.
So Brinell measures the size of the dent, Rockwell measures the depth.
Essentially, yes. And then for very small areas or very brittle materials like ceramics, there are Knoop and Vickers microindentation tests. These use tiny pyramid-shaped diamond indenters and very light loads. You measure the size of the resulting tiny indentation under a microscope, great for testing specific microstructural features.
And you mentioned a correlation with tensile strength.
Yes, particularly for steels, there's often a pretty good linear relationship between Brinell hardness, HB, and tensile strength, TS. There's even an approximate formula. TS in MPa is roughly 3.45 times the HB value. It's a very useful rule of thumb for estimations.
Okay, so we have all these tests, but are material properties always exactly the same, even within the same batch of metal?
Ah, an excellent and practical point. No, they're not. There's always some variability of material properties. Measured values will show some scatter. This happens for lots of reasons. Slight differences in testing procedures, how the samples were made, operator differences, equipment calibration. Plus, materials themselves aren't perfectly uniform. There can be tiny variations in composition or structure internally.
So how do engineers deal with this scatter? You can't just use one number if it varies.
Right. We use statistics. You typically measure the property multiple times, calculate an average value, and then quantify the spread or scatter using the standard deviation. When you see material property data plotted, it often shows the average value with error bars indicating ±1 standard deviation, giving you a sense of the typical range.
Which leads to the big question. How do you design something safely if the material properties aren't exact and maybe the loads aren't perfectly known either?
That's where design and safety factors come in. Engineers must account for these uncertainties to prevent failure. One approach is using a design stress, where you take the calculated stress in the component and multiply it by a design factor greater than 1. More commonly, you calculate a safe stress or allowable stress. This is often done by taking the material's yield strength and dividing it by a factor of safety, n.
So you intentionally design the part to only see stresses well below the yield strength.
Exactly. That factor of safety, n, is chosen based on many things. It's typically between, say, 1.2 and 4.0, sometimes higher for critical applications. A higher n means more safety margin, but it usually means a heavier, potentially more expensive part. It's always a trade-off involving economics, experience, regulations, and critically, the consequences if failure were to occur.
Wow, okay, so wrapping this up, we've really covered a lot of ground. From the basics of stress and strain that language engineers use, through elastic spring-back behavior governed by Young's modulus, to the permanent changes of plastic deformation defined by yield strength and onto tensile strength where nicking begins. Plus, vital concepts like ductility, the ability to demo, resilience, elastic energy storage, and toughness, the total energy absorption before fracture.
And we saw how true stress gives a more accurate picture than engineering stress, especially after necking. We looked at hardness tests, Rockwell, Burnell, Vickers as practical ways to measure surface resistance and even estimate strength. And finally, acknowledging that properties vary and how engineers use averages, standard deviations, and crucially, safety factors in design.
It really provides the foundation for understanding why certain metals are chosen for certain jobs, doesn't it? Making sure things work safely and reliably.
Absolutely fundamental. This knowledge ensures everything from tiny components to massive structures performs as expected, day in, day out. It's the science of reliability.
So here's a final thought to leave you with. We're constantly pushing the boundaries with new materials, complex alloys for extreme temperatures, nanoscale components. How might these fundamental principles we've discussed today, things like elastic recovery, strain hardening, maybe even the very definitions of stress at tiny scales, how might they evolve or be reinterpreted as materials become ever more sophisticated and multifunctional? Something to ponder. Thank you for joining us on this deep dive into the mechanical world of metals. We hope you feel better equipped to understand how these materials shape our world. From all of us here at the Deep Dive team, thanks for tuning in.